Hello everyone, today I'll introduce the paper called Motion Aware Graph Fusion Network for 3D Human Pose Estimation. My name is Yuan, and my advisors are Professor Xiaohui Yuan and Professor Chengyuan Zhuang. We all work in the COVID lab at the University of North Texas. The motivation of this paper is that most 2D to 3D lifting method implicitly assume high-quality 2D key point input. They trained and test that method mostly on clean 2D key point, either the 2D ground truth or 2D detection from fine-tuned 2D detector. This breakdown in realistic condition with occlusions or motion blur, where inaccurate 2D key point detection leads to temporal jitter and physically implausible pose. In this picture, on the top left, the spatial multi-head self-attention use global self-attention to learn the global spatial weight, and on the top right, our spatial graph attention introduce a graph-based inductive affinity using a skeletal adjacency matrix. And in B, on the top, the temporal multi-head self-attention encode models the long-range joint dependencies. And in the bottom, the temporal graph attention incorporates a self-attention refined temporal adjacency matrix, which is modulated with a logistic decay function to attenuate the weight for temporally distant frames. So the spatial graph attention is informed by the human skeletal graph. This means that the joints only attend to physically connected joints, with attention weight normalized by the node degree so that the highly connected joints do not dominate the aggregation. The temporal transformer applies a logistic decay weighting to self-attention to prioritize the nearby frames. This biases the model toward the local continuity, which is important for motion realism without losing the ability to attend to global context. This is different from the standard self-attention, which treats all the joints and all frames equally. Here we introduce the inductive bias tailored to skeletal structure and temporal smoothness requirement. We first embedded the sequence of 2D joint coordinates into a higher dimensional feature space and add both the spatial positional embeddings and temporal positional embeddings. We then integrate the prompt learning, which are learnable embeddings derived from the action-related semantic concept, such as arm's length action speed obtained from a vision language model like GLIP. The velocity embedding delta x is computed as a frame-wise difference in pose embeddings. We model global spatial and temporal dependencies using multi-head self-attention. Starting with the spatial multi-head self-attention, the input feature tensor is x where batch and time are flattened, and attention is applied across a joint within each frame. This allows the model to encode the global spatial relationships among all joints in a single pose. In parallel, we use temporal multi-head self-attention. Here, the input is x, where batch and joints are flattened, and attention is applied across time for each joint. This captures long-range temporal dependencies for individual joints. Both spatial and temporal attention use the standard transformer formulation with query keys and values obtained by linear projection of the input. To further refine pose features, we introduce fine-grained prompt learning in the first encoder layer only. In this step, the transformed pose feature X act as queries, while a learnable prompt matrix P provides keys and values. And finally, the prompt's refined features are not normalized, gated, and added back through a residual connection. This ensures that prompt learning refines the pose representation without overriding the original spatial temporal structure. Let human skeleton be a graph where Vs denotes the joint within a frame and ES represent the edge connecting the joints. In the spatial graph attention block, the degree normalized adjacency matrix AS is defined as AS of ij equal to 1 over square root of degree I times the degree j, if I equals J's or I and J's are connected, otherwise 0. The velocity is aggregated as delta x equal to a hat s times the vs of delta xs. Let human joint trajectory be a graph where vt denotes the joint across frame and et represent the edge connecting joints. In the temporal graph tension, the adjacency weights are defined via a logistic decay function, where at of ij equals 1 over 1 plus exponential of alpha t times the absolute value of I minus j minus beta t. This prioritizes nearby frames while still allowing longer-term dependencies. Temporal self-tension is then applied, modulated element-wise by AT, followed by the residual connection. After processing, we fuse pulse stream and motion refinement stream output at a velocity level with the equation delta x equal to gamma 1 element-wise multiplied with the delta x of the transformer stream plus gamma 2 element-wise multiplied with the delta x of the graph stream, where gamma 1 and gamma 2 come from the softmax of the learned linear transformation over the concatenated velocities. This allows the model to adaptively trust either the semantic rich whole stream and the smoothness enforcing motion refinement stream, depending on the reliability of each. We then update position by integrating the fused velocity x at t equal to x of the transformer stream at t minus 1 plus the delta x at t with x at frame 1 equal to x of the transformer stream at frame 1. And our loss function combines three terms. The first is the weighted mean per joint position error loss, which is the accuracy of the joint positions. The second loss is a temporal consistency loss, which penalizes a sudden change in the velocity. And the third is the velocity loss, which is the mean per joint velocity error. The weighting factor lambda t and lambda v are tuned to balance the stability and accuracy. When trained and tested on a cleaned lab controlled to the key point input, GAtFuN outperformed all the state-of-the-art method in both the diffusion and non-diffusion based setting. The model is trained on a clean 2D key point of human 3.6 using fine-tuned stack-out glass key point detector and test on noisy 2D key points from off-the-shelf Detectron 2. GAtFuN struck a balance between the spatial accuracy and temporal smoothness, while methods such as postmember achieve smooth motion trajectories by sacrificing the accuracy. In the diffusion-based setting, GAtFuN lacked in spatial accuracy and effectively managed temporal inconsistency. This video shows the qualitative result comparison between GAtFuN and other state-of-the-art methods. All skeleton-based methods, including GAtFuN, was trained on the 2D key points from a fine-tuned CPN or stack-out glass detector, with the consistent data preprocessing on the lab-controlled human 3.6 dataset, and they were then applied to the 2D key points from off-the-shelf non-fine-tuned Detectron 2 for the 3DPW in the white videos to demonstrate the robustness. In conclusion, this paper presents a motion-aware dual-stream network that integrates the joint velocity modeling and spatial temporal fusion for tracking human motion in 3D. The method captures the topological relationship of human skeleton and the kinematic continuity of motion to mitigate the motion jitter. Our method reduced the error by 7.8% and 6.8% in mean per joint position error and p-mean per joint position error on the human 3.6M dataset. On the MPI dataset, it achieved mean per joint position error of 14.1 millimeter, percentage of correct key point of 99.1, and area under curve of 87.7%. on 3D PW dataset, it achieves superior temporal smoothness with a mean virtual velocity error of 7.8 millimeter and acceleration of 6.1 millimeter. For real-world application, the non-diffusion model delivers real-time performance with a competitive accuracy, making it suitable for latency-sensitive application. This is our reference papers.